So welcome back to the WIMP discussion, which is really going to be your third lecture discussion period. Due to some conversations at lunch that several of you had with me, it was brought to my attention that when I wrote my lecture notes, I had made an oversight. It wasn't that I wasn't aware, just, you know, when you're putting together so much information, you always forget something. So I don't mean any offense to anybody in the audience who has a favorite experiment, but I actually made a big oversight. I did not show you the latest ANICE results, which came out just this last spring. So rather than jumping right into the liquid nobles, we're going to take a moment to review the ANICE results. And the ANICE experiment is primarily like a Spanish experiment. It's located in Canfranc Laboratory in Spain. It is very similar to DAMA and to, oh my God, my mind has drawn a complete blank. The combination of it's chems plus DMIs equals cosine, yes, the cosine experiment. It is getting late for everybody, I see. In that it also uses sodium iodide crystals and looks for a modulation signature. And so they basically had an array of 9 modules, 3 by 3, using really pure sodium iodide powders in order to grow their crystals, housed in these. Anytime you see these pictures, like the picture on the front page I have of one of our CDMS detectors, you'll notice copper is so shiny and nice. Always, this is like an oxygen-free, very pure kind of copper. It has nice conductive properties, and usually we're looking for stuff that's radio pure as well. They have a Mylar window that they can use to help do low energy calibrations of their detectors. And similar to DAMA and to cosine, it has photomultiplier tubes to read out the scintillation. So they use Hamamatsu photomultiplier tubes. And just like any other experiment that's using photomultiplier tubes to do dark matter, these photomultiplier tubes, or PMTs, have to have very low background and high quantum efficiency because remember, it's like 10, photoelectrons per keV of energy. So one of the things that ANICE did is they actually made sort of 3 different background models for what their backgrounds could be. And so these are plots of their backgrounds, and then some of the lines here are fits for some of the modeling that they did. And so you'll notice there's this M1 data set and this M2 data set. And the M1 data set's in a higher energy region, and the M2 data set is in a lower energy region. So you might be wondering why this is. And it's because when you're doing this type of work, what you really want to do is you want to model your detector as best as possible in your region of interest. And if you remember, the region of interest for DAMA and where they were seeing their signal is a sort of 2 to 6 keV energy bin. If you're blinding your data, right, how do you get any events or any kind of events you can look for in that region? One is to use sort of events that you know to be a background. So these are events that like multiply scatter. If you have an event that multiply scatters, it's not a WIMP. WIMPs will generally scatter just once. They're called single scatters. I see your hand. And up in this plot here, M1, these are events that are outside the region of interest that single scatter. So you can see that their background model fits both single scatter events at higher energies and multiple scattering events that are in their region of interest. Yes.
A question probably only a theorist would ask, but what does blinding your data mean?
Oh, that is a fantastic question. I'm so sorry. Like, it didn't even occur to me that someone would know this. But what it means is that, so you know that we're all biased, right? So the idea is you want to develop your analysis, like if you're making any kind of selection criteria or you're doing anything with your analysis, you want to take events that you're going to actually search for your dark matter in, like believe like this is where your dark matter window is. And you want to somehow remove it from the analysis so that you can't see it as you're developing the analysis. And there are multiple techniques for doing this. And I have to be honest, I don't remember which technique ANICE used, but you could go to a whole workshop for 3 days on blinding techniques. So you could do things like they call salting your data, where you take fake events and you salt it in, and then you work out your analysis tools, and then you remove the salt and get your results. Another thing, sometimes people will like take all the events and scramble the timestamps. Or you might actually just take all the events in a certain energy region and just remove them from the analysis. So essentially, usually one person or a couple of people who are on the blinding team in analysis will have the key and will be kind of removed from doing a lot of the development because they already know the answer. Although I don't think you really can at that stage. That's what blinding means. So that was a great question. And if I use any jargon you don't understand, make sure to stop me. All right, so these are the results. And so looking at the different energy regions, and 1, 2, and 3 here corresponds to background model 1, 2, or 3. You know, they have their chi-squared divided by their number of degree of freedom, the number of nuisance parameters they use. But this is what is probably most interesting for you. This is the amplitude of the modulation that they would see. So this is what they saw in their data. And so basically their data supports the absence of a modulation in both energy regions that they looked at, 1 to 6 and 2 to 6, and using all 3 of the background models. They're compatible. And so over here, you're just looking at the modulation amplitude, and then the 1 to 6 to 2 to 6 KeV region, the Dama Libra result, the Anise best fit, and then the colors here correspond to the 1 sigma, 2 sigma, and 3 sigma sensitivities of their 3-year exposure. So their best fits are incompatible with Dama Libra at 3.3 sigma in the 1 to 6 KeV region, and then 2.6 sigma in the 2 to 6 KeV region is what they report. So still, we haven't had a confirmation of Dama Libra. I think what will be more exciting is that they're planning within, so the way that they look at this, so with 5 years of data, they will be able to say something about the 3 sigma claim region of the Dama Libra, and then in 10 years of total data, they could say something at the 5 sigma level, is what they report in their paper. So going on to the liquid nobles. And again, like I had mentioned, I am not going to be able to cover every experiment, but if there is something you're interested in, make sure to ask me about it. And I'm generally going to try to explain to you how these technologies work and some of the physics behind them. All right, so the first thing with liquid noble experiments is thinking about the properties of liquid nobles and why we might want to use them. Generally speaking, traditionally 3 different nobles had been considered for dark matter detection over the past few decades, xenon, argon, and neon. At this point, nobody is really talking about a neon dark matter detector anymore, but certainly large detectors that are made of either liquid xenon or argon are still being considered. And so the reason that these properties are important is that many of their properties determine various aspects of the experiment design. One example would be like xenon here has a high density and a large target mass. That's very favorable. That's what you want in your dark matter target. But it's not very abundant in the atmosphere, which means it's a little bit more expensive, you know, to try, you know, to collect and then use. The energy loss of an excited particle in liquid nobles is shared between excitation, ionization, and the sub-excitation of electrons that are liberated in the ionization process. And so the average energy loss in ionization is slightly larger than the ionization potential, which is, you can think of as the gap energy. And so as a result, the ratio of the W value, which is the average energy required to produce an electron ion pair, compared to the ionization potential or energy gap, tends to be between 1.6 and 1.7. And so you can see for the different argon, krypton, and xenon here, what that ionization potential is, what the W value is for both gas and liquid. And so this is another property that people look at when they're thinking about these experiments. So how is it that you get an ionization signal in a liquid noble? So I've written this out two ways. One is I like schematics like this. And so in this here, I write xenon, but you could kind of replace this with argon and you would have basically a similar thing going on. Over here is written out as a series of equations like you might write in your PhD thesis. And here R could be either xenon or argon. But basically this maps exactly over to this. So the idea is that in the liquid noble, you will get either an electron or a nuclear recoil happening. When that happens, the energy is deposited in sort of three different ways. You get a little bit of atomic motion, so this is heat that's lost, and you kind of just lose that in the process. And then you get excitation of the element, and you get ionization of it to an ion, okay? So let's start with the excitation. So essentially, you get excited by excitation and you essentially form a dimer state, okay? And then this relaxes down. And eventually what you get in this relaxation process is scintillation of light. Another process that's going on at the same time is the ionization. So you ionize the xenon ion and you can get at this very first step here, you can get escaping ionizing electrons that could produce your S2 signal. But that also, in parallel, you also most of the time will end up essentially going down this process where you capture an electron and then it recombines, and then you go back up into this excited state again, where again you have this relaxation down, and you end up again with S1. Okay, so you get sort of a couple of processes that are going on in parallel, both which give you some sort of emission. So then if I have my T, yes.
Sorry, thanks. On that schematic, were the number of asterisks showing how excited the xenon is?
Okay, so just a second here, let me think. I forget what the second one actually means. Okay, so the second star means that it's a dimer. It just means it's a dimer, which is a type of chemical process.
Okay.
Yes. So the two stars here mean this is a dimer state. Okay. Just checking my notation. So liquid noble detectors. So the idea here is that then you basically take, a big container of liquid xenon, and then you have on top of the liquid xenon, you have a gaseous state. So you have a liquid state, a liquid, and then you have some of it in a gaseous state. When a particle comes in, interactions in the liquid produce that excitation and that ionization. And that leads to scintillation light emission. That's your S1 signal. Those electrons that are produced are then drifted up into the gaseous region where they produce a second scintillation signal. So that second scintillation signal is proportional to S2. So we call that the second signal. And then you have PMTs at both the bottom and the top of the array that read out those signals. And so if you take a look at the distribution, and I guess by distribution, I really mean you take a look at the height of the pulses between the S1 and the S2 signal, WIMPs, particles that interact with the neutrons, or the nucleus, sorry, not neutrons, but the nucleus, give a ratio where the two pulse heights seem to be sort of equivalent. But if you have an electron recoiling event, the S1 signal is smaller than the S2 signal. And so this gives you your discrimination by taking the ratio of S1 to S2. Now, the other thing that you can take a look at with these two scintillation signals is that clearly, like I can get XY positioning from this, right, by my PMT readout. But then if I pay attention to the drift time between the first signal and the second signal, I get a Z dependence. So with these detectors, you can get the XY coordinate to some amount of precision, from, or not just XY, but XY and Z position of the first interaction. Sorry, yes.
So you said after the ionization, you end up with another excited xenon, which
Right, so it can go
so
back
it's
down, yeah, so S1 is a combination of both the ionization and the excitation, but S2 is just those electrons that come off of that excitation where the electrons are drifted up into the gaseous phase, and really, when they hit the gaseous phase, they get like accelerated, and that's what causes the S2 signal.
okay, but these S1 signals, they're close enough together that you see them basically at the same time?
No, you see them at different times. That's why you can get a Z dependence of where the signal
The
originated.
S1 is like really close by. The S1 is not spread out. But that's, I think, what you.
Yeah, the two S1 signals that you have.
Oh, yeah, no, they're very close in time, yeah. Sorry, I misunderstood.
Okay.
I misunderstood. I thought you meant the difference between S1 and S2. My bad, because both of that process that comes down and then re-excites to go back to S1, that happens very fast. And so that's just part of S1.
Okay, thanks.
No problem. All right, and so here I'm kind of showing the 3 leading experiments that are really aggressively in xenon competing now. And I apologize if anyone in the audience is a big fan of the argon experiment. There's an argon experiment out there doing similar things. You would see similar plots, but I'm not going to be showing it today because of just lack of time. But the basic idea here is that each of these 3 plots, so this column here is xenon 1 ton, this column is Lux, and this column here is Panda X2. And so what you're getting is in this very first row of plots, these are data from calibration. And in all of these plots, the blue solid line is the median or the mean, if you will, of the electron recoil band. And the dotted blue lines indicate the sort of sigma. This is the region that's taken as the electron recoil region if you're identifying events. The red solid line is the median or the mean of your neutron or your nuclear recoiling events. So here you can see very nice fits to bands of electron recoiling. In the second row, the same thing for nuclear recoils, except for this time, the red solid line is the median of your nuclear recoil band with the dotted lines showing you the bands. And this again is neutron recoil data. Like these are neutrons from a calibration source. These are electrons from a calibration source. The third row is showing you the data from their most recent runs that were looking for a traditional WIMP analysis. So all of these experiments do all sorts of different analyses. This is your traditional WIMP analysis, not necessarily the most recent result that's on the archive. And so what you can see is in black here are the data points. And you can see that in all 3 cases, the data points primarily are lining up with events that would be electron recoils, so they're backgrounds. Yes.
John, I have a question on the previous slide. I don't understand how you get sky localization information. Could you please explain it in a bit more detail?
Get which information?
Sky localization.
The
X, Y, Z,
Z.
right?
Okay, so this is an array of PMTs. So imagine, if you will, you have a cylinder. You have PMTs on the top, like a number of them. You have PMTs on the bottom. So when your signal reaches the PMTs, like in this case here, you can see that the PMTs in red here is the location that gets the most photons from the signal. And then blue is like least or fewest. So from this, you can reconstruct an X, Y position of where the event happened. So this S2 is going to happen essentially directly above S1 because there's an electric field running usually in this direction that's accelerating your electrons, up towards the top. And so they're not really going to waver much. They're mostly going to go in a straight line. So the light's going to get collected by, some number of the PMTs that are in the location that's directly above where the event is happening. The Z happens because the timing between S1 and S2 is going to vary. So this gaseous region is not very large. The liquid region is much more larger. And so if the particle interacts down here, it's going to take a longer time to reach the gaseous region to make the S2 than if the particle interacts up here. And so by looking at the time difference between S1 and S2, you get the Z dependence.
Yeah, I understand the time dependence part, but I don't understand, like, you have so much stuff that's being thrown at the top of the detector. I don't know how you can differentiate what's coming from where.
I mean, I don't quite understand what you mean by you have so much stuff being thrown at the top of the
I mean, you
detector.
have like lots of, I don't know, cosmic rays or whatever. that's
Oh,
coming
no, no,
at-
no. So if the cosmic ray comes, the cosmic ray again would interact in the detector volume, produce an S1 signal, be drifted up, produce an S2 signal, and you still would get, you know, some measurement of the location of where that event happened. So this is like for a single event at a time. So if you're talking about lots of cosmic rays coming in, like this is essentially, you know, going to trigger. Each event is going to trigger and produce an S1 and an S2 in the detector. And it will, I want to say like reset, but essentially you're resetting with each event. These detectors probably operate at something like a hertz or a few hertz event rate. So your event rate is not that large that you can't collect them. Now it is possible that you could get two events happening at the same time simultaneously and then going up. So in that case, you can see that you have a multiple event in the detector. And then because what you would end up is you'd end up with one red region, and over here you might end up with some yellow and blue around it. And you would end up with, you know, weird things going on. And you can identify that and tag it as like two events happening at the same time or a multiple scatter of some sort. Like if you have a neutron coming in, there is some small probability that it could scatter twice in the detector. So those are certainly signatures that could happen, but they're not very frequent. You have to realize that the cosmic rays, you know, we beat those way down. The shielding is taking care of a lot of this.
I just have a comment. So for cosmic rays, right, you know they're coming from outside, and we have this thing called the muon beetle.
Mhm.
So if then the muon beetle will light up first, so you know it's coming from outside, and then we just throw the events away.
Right. But I think he's trying to,
Yeah.
okay,
Use this instead of laser.
sure.
Does that answer your question, no?
Yeah, mostly, I mean, I've considered this one example. I mean, just like you have a very
You're right. No, we have tons and tons of events that come into these detectors. And the point is that the way we distinguish that's kind of was the whole point of talking about these lectures, that really almost all of the events that we're seeing in these detectors are electron recoils from backgrounds from outside, and then identifying where those background particles are coming from. But regardless of where the background particle comes from, the particle has to interact. Oh, it doesn't have to. The particle is going to interact if it gets to the detector. It's going to interact in this liquid xenon and produce a signal, and it's going to get accelerated upward into the gaseous region. And then it's going to produce a signal like this. So this is one event. My next event may come from this direction, interact here, accelerate up into the gaseous region, and then produce like lots of red hits, if that, you know, looking at the schematic, with yellow around it here. So I would know that with some different, you know, depth, timing difference between these and over here. And so that would be event 2. And then event 3 is going to come, and it's the same thing. So each event gets tagged in the detector with this information recorded.
I don't know, makes sense.
And so I think what it is like, I guess my impression of what your question was is like, can the detector keep up with the rate that these events are coming in? And the answer is yes, it can. And a lot of it is because the backgrounds get beat down to such a level that the events are not happening all that frequently in these detectors. It's not like Atlas or CMS or any collider where you're just having tons of events coming out of a single interaction. And we're not recording single electrons, obviously, like or photons, right? Like it's a collection of them that produces a pulse for this event. Yes.
Sorry, I'm just trying to clarify what he means. I think I understood that he is asking for directional information, I think. If we can, is that true maybe?
Okay, so yeah, okay. So if you're asking, can we track, like, we're not tracking an event or a recoil through this medium. Like the interaction just happens and everything, the light goes off and stuff. So all that this information, this XYZ information is telling you is the location that the interaction happened, it's not a trap. Does that, if that was the question. I'm not sure if I've answered your question or not.
I don't know my question.
I guess then my question to you is do you have any other questions? Is everything perfectly clear?
It's never clear, so.
And I hope I don't sound like I'm yelling at you. I get very excited because I find this interesting. And so I'm really not yelling at anybody. I'm just very excited. All right. Okay. Oops. Okay. So onto this, we have, are we okay with this one or can I move? Okay.
Okay.
Go ahead, go ahead.
It might be a question more maybe directed to the people because it seems like
The two bands. I think I know what you're gonna ask.
okay, so it seems like the two bands are overlapping quite a lot. So I assume you define the region of interest rather strictly, something
Yeah.
like only at the mean of the nuclear recall band and downwards or something like that.
Yeah, so I can answer at least this partially, and if someone from Xenon then wants to add more clarity, that's okay. But the answer is, I mean, you know, obviously being a germanium person, this is where I was always like, yeah, we're so much better. The separation is more. But in reality, I mean, if you want to really be honest about it, there was a time where you would restrict the region, do cut and count, and have some probability of how many overlaps, like how many events from the electron recoil region leak into the nuclear recoil region, and then you would do a cut and count analysis with it. But now we use these sophisticated techniques where we know like so well what we think our backgrounds are and at what rate they are, and we make models of them. And then we use profile likelihood analyses and other types of multivariate analyses to help separate them out. And those analyses have a lot of rejection power in them when you feed them good models, which we are so much better at now than we were when I was a postdoc, 15 or 20 years ago. That this is enough separation to be able to get you good results, like using analysis techniques and your understanding what the background should look like.
Oh, yeah, we
Did you want to add something more? Wait.
Yeah, the red line is the median of the NR band. And you're absolutely right that for low S1s, there is a substantial leakage of ER events into the NR band. And then we also use the profile likelihood method because, mathematically speaking, because of the Niemann-Pearson's theorem, that's the most powerful test you can have for simple cases, simple hypotheses, but it also generalizes to like more complicated hypotheses. Yeah, that's all, simple.
Okay, so let me talk a little bit more about these experiments. So one of the things that I want to talk about is energy. So, it's great that we have this discrimination and stuff, but of course, what you want to be able to do is understand, what is the energy you're getting and what are the factors that you need to think about, like maybe as a systematic or as a potential source of errors when you're making these estimations. So nuclear recoils are measured through a combination of scintillization and ionization. So the nuclear recoil energy is related to this first scintillization. So this is in a unit we call KeV-NR, which means nuclear recoil. And I'm going to talk some more about this in some more detail and tell you, a bit more about transforming things when we talk about the solid state detectors. This is the observed scintillization in photoelectrons. This is the light yield in photoelectrons per keV measured as an electron particle. So that's sort of what you can think of as are you doing it as like a neutron or a nuclear recoiling particle or an electron recoiling particle? This is the scintillation efficiency of nuclear recoils in liquid xenon. So something that you measure. SE is a suppression of the scintillization due to the electric field for electron recoil events. S sub R is the same factor, but for nuclear recoiling events. So this is the formula that takes your S1 signal and transforms it into nuclear recoiling energy. So L effective, like I said, this accounts for the quenching of the scintillization signal for a nuclear recoil. So this again is something that gets measured. It's the S1 signal measured as a function of nuclear recoil divided by the energy of a nuclear recoil divided by the S1 signal for a 122 keV gamma line from a cobalt source divided by 122 keV. So that's something that gets measured. The nuclear recoil energy then, how is it related to S2? So the energy here is the observable scintillation in photoelectrons divided by a factor that they call Y. This is a secondary amplification factor. It's in photoelectrons per electron. And then also divided by QY, which is a factor of, or is a function of energy. This is the number of free electrons per unit energy. So these are the formula, and there is a whole paper that the Xenon collaboration wrote on how they do the calibration and how all of these formula work. So if you're very interested, I can give you that reference. So let me just briefly say the status of these experiments. So Xenon is now in the N tons phase, and they're taking data. So this detector was started construction, I believe, in 2019 and plans to run through 2025. And it's 8 tons of liquid xenon. And right now they're taking data. LZ is, and this is an experiment in Grants also. This is in the US, in the Sanford lab. They're in commissioning. They started building in 2019. They plan to run till 2025-ish. And this is 7 tons of liquid xenon. And so these two are really like competitive with each other. And actually Panda X is also another one that's very competitive. Like the 3 of these experiments keep rotating whose results come out first and whose results are a little bit better. So Panda X is now making in the phase of Panda X 4 ton, and they're also in commissioning. They started in 2019. I don't know what their plans are as far as current end dates of runs. Most likely it will be similar timescale to these detectors because these are all sort of similar size. And then finally, we also have under design this dark side 20K experiment. And essentially this would be like 50 tons of liquid argon. And so this would be a much larger experiment. Yes.
So when new direct detection experiments are being proposed, are they paying special attention to the region of the gamma signal?
Not really.
Okay.
We're paying attention. Remember that plot I had, I think it was in the last lecture, where the arrows went this way and that way? We're paying attention to getting down as far as we can to that neutrino plot and getting as low as possible mass we can in the other direction and also down towards the neutrino plot. I would say the only people who are thinking about the Gamma Libra region right now are those who are trying to replicate their results. That's at least the way I see it. All right, so let me move on to bubble chambers. These are kind of fun too. So the first thing is to ask yourself, how does a bubble chamber work? It turns out there's a couple of papers that you can find, like to talk about the basics of how this works, but you have to dig pretty hard in Google if you have at least my level of trying to search for these types of papers. But basically, let's just pretend here that we start with a bubble that's in thermal equilibrium and chemical equilibrium with the liquid around it. So if the pressure of the bubble to first order is greater than the pressure of the liquid, the bubble is going to expand. And in this case, I'm just saying this is not taking into account any surface tension. If I want to include surface tension, which is also kind of pointing inward, the bubble grows when the pressure of the bubble is greater than the pressure of the liquid plus the pressure of the surface tension, right? So far, this is pretty trivial. And then the second thing is that the radius of the bubble has to be greater than the critical radius. And so this is equal to 2 sigma, where sigma here is a surface tension term that you can look up for various fluids, divided by the pressure of the bubble minus the pressure of the liquid. Bubbles that don't meet this criteria collapse. Okay, so if you want to get the threshold for bubble nucleation or formation, it's given by this formula here. So this formula has a term for the surface energy, a term that is representative of the bulk energy, and a term that takes into account reversible work. So these are the very specific formulas that you could look up and read about or do in a statistical mechanics class on bubble formation. And so, okay, so what does this mean? So this is a plot that's the detector response versus the threshold energy for various different types of particles. So here you have 1.75 MeV gamma rays. This is the response you would expect from a 50 GeV dark matter particle. These are neutrons that are measured. So this is obviously simulated and not measured. And then over here, you have alpha particles and nuclear recoils from lead-210 particles. So the idea is that lead-210 is a very long-lived isotope. It has a half-life of like 26.5 years or something like that. When it decays, it goes through a series of decays that gives off daughter particles till you get to polonium-210, and then polonium-210 decays down to stable lead. I'm sorry, polonium-206, it decays down to stable lead-206, and when it does, there's like an alpha particle given off, and the remaining back lead nuclei also recoils like with a small amount of energy in the opposite direction. Okay, so that's sort of the chemistry of why people hate lead-210. Heavier particles have higher thresholds, so you can tune the response of the detector so that it's unresponsive to most electron recoils. And I think you saw that earlier today, was it, when we did the bubble chamber? And then, underground shielding is used then to mitigate things like neutrons. So I can take care of the gammas, the neutrons I mitigate, but what about these alpha particles? What do I do here? So remember the nuclear recoils. What do I do about these? Well, this is absolutely, in my opinion, the coolest thing ever. It turns out that alpha particles sound different than like neutrons and WIMPs. Isn't that the greatest thing ever? So essentially, honestly, so you put some piezoelectric sensors on the bubble chambers and you have your discrimination. So the idea basically is the alphas deposit their energy over like tens of microns, which is kind of smaller. The nuclear recoils deposit their energy over tens of nanometers. So that means that your alpha particles are 4 times larger than like the other nuclear recoils. And so that is what you can measure with these piezoelectric sensors. They're essentially just sound sensors. And so here's a plot. I think this plot comes from the Cooley collaboration, if I remember correctly where I stole it from, and is showing essentially what these particles sound like in a graphical form for basically a neutron source versus a wind search data. So these are neutrons, these are alphas. Great discrimination just by looking at how they deposit their energy in these sound sensors. And then these are just some pulses from the same plot. All right, so let me tell you a little bit about the status for bubble chambers right now. So it used to be that there were sort of 2 collaborations. There was the Cooley collaboration that used bubble chambers, and then there was this Picasso collaboration that used a super heated sort of gel, but the same basic technology. They have joined forces to form the PICO collaboration. And they have a series of detectors that they're in the current process of either having had results or producing results or going to produce results in the future. Their ultimate goal is to make a 500 liter bubble chamber. So the PICO 2 liter was the first, then came PICO 60, then came PICO 40 liter, which I know seems like it's going backwards, but one of the things that they figured out between PICO 60 and PICO 40 was that the way that they had their bubble chamber arranged actually caused them some background and some noise and some problems. So if they turn the bubble chamber upside down, it fixed their bubble. So that might be simplifying a little bit, but that's pretty much what they did. If you want to read details about it, go to my lecture notes where I explain it a little bit more fully. Yes.
This is a super basic question, but why don't the bubbles just float to the top?
I mean, why would they? I mean, essentially what they do is they just reset it, like by, changing a piston, but these aren't, I mean, like the whole vessel is under pressure. I guess I'm trying to think of the mechanism by which the bubbles might move.
I'm imagining, I mean, the gas is lighter than liquid, right? So,
But it's not a gas. It's a
Oh.
superheated fluid, essentially.
oh, okay. I'm
So
thinking about
the whole thing is a liquid.
Thank you.
Yeah. So think about maybe like, sometimes like if you shake your dish soap or something really well and you get the bubbles inside the liquid, I mean, those bubbles don't move very fast. Certainly not on the time scale that they're resetting it with the piston to repressurize the, after an event to repressurize the bubble chamber or reinitialize it. Okay, so now let me move on to the cryogenic detectors. All right, so let me just throw up all my words here. So these are really cool. These cryogenic detectors that detect phonon and heat. And this goes back to the question of like, how is it that you detect a phonon? So basically, I mean, the basic idea is that there are two families of sensors for a phonon signal, a thermal and an athermal sensor. So thermal sensors wait for the full thermalization of the phonons that is in the bulk of the detector. And in this case, the detector is the absorber. So think absorber equals crystal equals substrate. These are all interchangeable words that we use. And then for the sensor itself, athermal sensors detect the fast non-equilibrium phonons. Okay, so basically a temperature rise in the absorber is equal to the deposited energy over the heat capacity of the system. And so essentially what we do is we just put a thermometer on top of our crystals. So there are essentially two widely used technologies for measuring these phonon signals. One is an NTD or neutron doped germanium sensor. And the second one is a transition edge sensor. All right, so let me say a few things about NTDs. Okay, so NTDs are actually used by the Edelweiss collaboration currently. And so the idea is that you have a small germanium semiconductor crystal that's been exposed to a large neutron flux. And essentially the reason you do that is that you make a large controlled density of impurities in that little crystal that can help with making the measurement. So the NTD measures a small temperature variation relative to some T naught. And that T naught, then that T naught is set on the transition from superconducting and the resistance regime. So it's set there. And so it has a dependence, the resistance then basically has a dependence on temperature. So the resistance is just continually measured by flowing current through it and then measuring the resulting voltage. And those sensors are essentially just glued to the detector. So like, here's an example, just glued onto sort of a detector. And this is just a schematic. The second type of sensor is called a transition edge sensor. This is the technology that Super CDMS uses. And so the idea here is that you have this transition edge sensor. It's a thin superconducting film that's also operated near its critical temperature. So it kind of sits right here on the curve. Just both of these technologies need a refrigerator to keep the detectors cold to make the readouts work. So there's a heater with an electrothermal feedback system that maintains this temperature here at its superconducting edge. And then the temperature changes are detected by essentially a feedback current that's in a squid or a superconducting quantum interference device. Okay, so basically the idea here is an event comes in, it starts an interaction in the crystal, phonons are generated. These athermal phonons are then collected in an aluminum fin. This aluminum fin is another thin film that's on the surface of the detector. And since it's superconducting, the electrons are paired together in Cooper pairs. When you add the athermal phonons to here, you're essentially adding energy. So that breaks the Cooper pairs. And you end up with like quasi-particles that diffuse across this aluminum fin into the TS, which then heats up, goes off of its critical curve, and then the squid and its feedback current resets everything. The squid reads it out, and then feedback resets it. So let me tell you a little bit about the super CDMS detectors and also tell you a little bit about the Edelweiss detectors and where they are. So currently, super CDMS is in the stage of constructing their experiment at Snow Lab. We're going to have an initial payload of 4 towers. Each tower is going to have 6 detectors. So this is going to be a total of 1.39 kilograms of germanium and 0.61 kilograms. That's supposed to be silicon, not is. Apple autocorrect. And each of those are 100 meters in diameter and 33.3 meters thick. So we have 2 detectors called high voltage detectors, or 2 towers of high voltage detectors of both the germanium and silicon variety, 2 towers of ISIP detectors of the germanium and silicon variety. And so the layout of the sensors is slightly different for the 2 detectors, but I think for this class, most people don't care. So we'll go past that. But what you would care about is sort of what some of this might, yes. Oh, I'm so sorry, I didn't see hands. I'm so excited.
No problem. Can you go back to slides?
2 slides. Maybe. That
Yeah,
one?
so this one.
Okay.
It's just because I'm not sure I understood this. I mean, I understand that the phonons sort of break these Cooper pairs, but I don't understand how the fact that they are broken sort of allows the conduction, the diffusion in that diffusive region.
I mean, this is just a schematic. They're diffusing everywhere.
Right.
Okay, so it's not like there's any, I mean, there's no like electric field or anything that's making them go into the TS. This is just a cartoon of the fact that once they're broken, they're quasi-particles, and I mean, they're going to diffuse,
Okay.
right? And so they diffuse and are collected in the TS. But it's not that the diffusion only happens in one direction. This is just the cartoon.
Okay. But I mean, that doesn't happen evidently when they are Cooper pairs.
Well, yeah, when they're Cooper pairs, they don't diffuse into the TS. They're just paired up, and
Okay.
I mean, they may be, moving about or hanging out in the aluminum, but they don't go into the tungsten and start heating things up.
Okay.
It's not until you dump more energy into it, it breaks the Cooper pairs, creating quasi-particles, and those quasi-particles diffuse into the TS.
Okay. And can you also like measure the phonon energy in this fashion?
Yeah, this is exactly how we measure the phonon energy.
Okay.
So this heats up essentially. So it changes, again, heating it up makes it go into the normal regime where you have some resistance essentially. So that temperature change is measured by a squid essentially.
Okay.
And so you can measure how much essentially heat you're getting, if you will, from the squid.
Okay. Okay, thanks.
Yeah, no problem. So it's all about that. I mean, the idea behind these 2 different schematics of detectors is really quite the same. It's 2 different ways to measure the heat. The difference being that the transition edge sensor collects the athermal phonons and does its measurements that way, where the bolometer collects thermalized phonons. That's sort of the difference. All right, so let me tell you about the 2 different styles of detectors in the super CDMX experiment. So the ISIP detector is the classic detector that CDMS has been running for many years in different configurations. And basically, On each detector face, you have phonon sensors, which are represented in blue here. And then it's not very easy to see, but there are these red charge bias lines that are in between. So the phonon sensors are the ground. And then on one surface, the charge sensors are positively charged, and on the opposite surface, they're negatively charged. And just to show you sort of a blow up. So if I take some of these, so these are transition edge sensors. So the gray here, these are the aluminum fins. In blue, you're seeing these transition edge sensors schematically represented. So these are essentially the thermometers on a CDMS detector. Is your hand up? We're just stretching. Okay. Oops, sorry. So in standard IZIP mode, the basic idea is your particle comes in, it interacts. You get recoiling phonons, you get electrons and holes. You're measuring both of these. And when you do that and you do your ionization yield versus your recoil energy, you get very nice separation. So up here, these are gammas that pass something called a charge symmetry cut. So let me say a moment about this. So because you have ionization sensors on the top and bottom of your detector, any event that happens in the bulk of the crystal is going to have symmetric charge collection. But if you have an event that happens near the top of the crystal, because remember you have a ground followed by your charge line followed by a ground, you set up like a micro field near the surface that keeps the charge collected primarily on one side. And so we call that asymmetric charge. In that case, it's an event that's occurring near the surface, and these can be really problematic because they can suffer from incomplete charge collection, and then they can mimic our dark matter signature. They kind of are these sorts of guys in red here. These are events that are electrons that are happening near the surface, and as you can see, they like kind of slump down a bit. And the worry is how many of them end up in this green band, which is the nuclear recoil band. And so it turns out that we really do a good job. So this is like a super blasted detector with backgrounds, just to illustrate how good the rejection is with those detectors for separating out the two types of events. So the high voltage detectors are a little bit different. So essentially what happens is that when you drift electrons across the potential, you actually create a large number of phonons. So when I first started in CDMS, I didn't know anything about solid state physics, and I didn't even know what a phonon was. And I had a postdoc at Stanford tell me that phonons are just like photons. And I realized within about like 3 seconds that this is absolutely not true. Photons rarely multiply. Phonons seem to replicate like bunnies. So if I put an electric field across my detector and I have this interaction, I'm going to get my electrons and holes and some primary prompt phonons that occur. And then as the charge is drifted through the detector, I get these Luke phonons is sort of shorthand for what we call them, or LTN or NLT phonons. And so my total phonon energy in a high voltage detector is the primary recoil energy plus the Luke phonon energy. And the Luke phonon energy is the number of holes times my voltage bias times the electric charge. And so the reason that we do this is that we can get ultra high resolution through this type of measurement. And so in the super CDMS experiment at Sudan that we ran when we were preliminarily trying out this type of technology, we were able to get thresholds as low as 75 EV and 56 EV in the electron recoil. Okay, the trade-off here, and so what you can see, like in this here again, this is the rate versus the energy, and you can see we can see K shell lines, L shell line, and way down here an M shell line. So it's really a beautiful sort of instrument. But the trade-off is that we have no yield or detector phase discrimination when we're running in this mode. Now let me say something about units. I'm guessing at this point, you're pretty frustrated with what is a KeVEE and this KeVNR. Isn't a KeV a KeV no matter which way you look at it? Well, sort of. So on units. So we know that these loop phonon energies is given by this equation. We've already done that. And we know that the number of electron hole pairs generated in an interaction is given by the recoil energy divided by this factor epsilon, which depends on what type of material you have. In germanium, it's 3 eV. 3 eV of energy is required to create one electron hole pair. And we know that the total phonon energy was given by this equation. That's all from the previous slide. And so nuclear recoils produce electron hole pairs less efficiently than electron recoils. And so when we take this into account, we define a yield. This yield parameter is defined as 1 for electron recoiling events. So the number of electron hole pairs that I get is the yield as a function of recoiling energy times the total or the recoil energy divided by, the energy it takes to create one pair. All right, so then I can rewrite my total energy as the electron recoiling energy, or I'm sorry, as the recoil energy times the quantity 1 plus the yield times E times my voltage bias divided by this epsilon number. So then if we calibrate our detectors using electron recoiling events, so like say we take a gamma source and we calibrate it, the resulting energy scale is KeVEE. To convert this to KeVNR, we have to essentially equate the nuclear recoil formula to the electron recoiling formula. So we take the ER here, or this R here, and we make it nuclear recoils. And then we set that equal to the fact that if this E were from electron recoils. And then recalling that we define the yield as 1 for an electron recoiling event, we get to a conversion formula between nuclear recoil energy and electron recoiling, or electron equivalent. The EE stands for electron equivalent, in case you're wondering why it's not ER. Just more jargon. All right, so then it seems like it's really important that we determine what this Y factor is, right? Some people call it a quenching factor. So there's 2 ways you can do it. You can either model it or measure it directly. And so this plot here is the ionization efficiency. This is the yield, the Y, or the ionization efficiency, the Y, versus the recoil energy. And you can see that lots of people have tried to measure this and that the data points seem to be all over the place in some cases. Several people have also tried to model this. Juan Colar made a model once, and that would be the red dash line here. And other people, we have made a model at one time of it. But there is a popular model that most people accept, yes.
So do you care about like Y as a function, or do you only care about its specific values for the nuclear?
We need it as a function because remember our recoil energy that we're measuring in different particles spans a scale. And one of the things that worries us a lot is notice there are no data points at these low energies where we're trying to go down to sub GeV, for example, measurements. That's concerning, and we, at least in super CDMS, are trying to make some measurements down at that level. Yeah, so the model that is most utilized comes from Linhard, and the model is that the yield is equal to K, this parameter K times G, divided by 1 plus K times G, and G here is, you can see this is nothing but some kind of functional form fit. And it's dependent on material, or actually this actually works in germanium here, but it's a functional form that people use. And basically this value K here is a number that you pick and parameterize. And you can see here on this plot if you pick a K of 0.1 versus 0.159 versus 0.2, you can see the differences that you get in your model. So here's the green, here's the blue, here's the pink. And this seems like a very specific number to put on the spot. And the reason is because this is the number that we use in germanium. And as you can see, it kind of gives a very reasonable, good fit to the data. All right. This slide is not supposed to be here. That was a model that one of our PhD students did for super CDMS detector. And at this point, we're just going to skip past it. But the point is you can make your own model if you want. So let me just show you what this means. Like when you're looking at this plot, so this is the ionization energy in keVEE versus the recoil energy in keVNR. And so what you have here, these are events from a barium source. And this here in gray are events from a neutron calibration source, okay? And so these lines here are kind of like lines of true energy that map from the keVNR scale to the keVEE scale. And so what you can see is that this 10.4 keV line, which comes from the excitation of germanium because of those cosmic rays that are so pesky. Okay, so that's what this big blob of events are. And so you can see this is something like, 10 point something, 10.4 according to my notes, on the keVEE scale. But if I go to the nuclear recoil scale, it's down, nuclear recoil scale is down here at like 16. So it's a little bit confusing, but it's because there's this inefficiency when you are looking at nuclear recoils versus electron recoiling types of particles. Where am I on time right now? Let me kind of skip past this. I mean, yes, go ahead.
I did not understand what that diagram.
Oh, it's constant energy. So like, let me see if I can get this to go back. It's constant, it's sort of like a line of constant energy. So like, yeah, I mean, don't worry about it. The point was to try to show you how you could map from one scale to the other. I think my lines of constant energy did not quite work out the way I wanted them to. All right, so super CDMS is now going to, oh, I'm sorry, there was another question.
Hi. Yeah, so you have ERs and NRs. So ultimately, how are you going to perform your signal to background discrimination?
What do you mean how? Oh, you're taking the ratio of electron recoil to
Also-
nuclear. If you're going to discriminate between backgrounds with an IZIP detector or any kind of sort of detector that has a discrimination, you're going to base it on yield, which is essentially your it's a function of recoil energy versus yield, which is the dividing of the charge energy divided by the nuclear recoil energy is the quenching factor.
Or the Y?
Yeah, and so in germanium, Y is 1 for electrons and Y is around 0.3 for nuclear recoils. And obviously there's a little bit of spread there, but that's where the mean is. So if you're going to do your discrimination, that's it. So remember way back, I had those discrimination lines and they're straight. Yeah, that's it. The electron recoiling events are going to have a yield of 1 with a little bit of spread. And nuclear recoil events are going to have a yield of 0.3 with some spread.
Y equals to 1 for ER, but that's by definition.
Yeah,
right?
you just defined it that way.
Also, you
You
normalize-
could define it somewhere else, but you just do the same calculation again.
Okay, so you normalize the Y for NR according to the ER, the Y for the ER.
All right, so let me go back here. I think I'm. Sorry. Okay. This is the formula you would use to convert between, like if you're looking at an event by any kind of event, if you want that event energy to be measured as nuclear recoil, this is the conversion that you could use. So if we're measuring the phonon energy the phonon energy, automatically sort of measures in recoils, right? This is the electron equivalent energy. And so you just use this formula to convert back and forth.
Okay.
I mean,
yeah.
you would have to do something similar in xenon because you have, you're measuring something with photoelectrons and you're trying to get your energy units to be consistent.
As in xenon, our discrimination space is in CS, okay, S2, S1.
Yes.
And then it's a two-dimensional thing, and then you just see what your events are.
Yeah.
Then,
So this is your chart, our discrimination space is charge energy divided by recoil energy, right? Okay, so phonon energy as a function of phonon energy. So it's just like what you do with S1 and S2, but we do it with the amount of energy you measure in the charge sensor divided by the amount of energy you measure in the phonon sensor. That's the yield on the y-axis. And on the x-axis is for that same event, what is the phonon energy we measured?
Okay, okay.
So it's phonon energy. I mean, you can think of it as, yeah, so you're basically taking charge energy divided by phonon energy as a function of phonon energy. And Edelweiss would do the same thing. Kress would do scintillation energy divided by charge energy. Actually, what do they do? No, sorry, phonons. Sorry, I was like, they have phonons. They don't have charge. So it'd be phonon energy divided by, light energy, scintillation divided by phonon energy as a function of phonon energy.
I mean, I guess I'm just wondering why you bother dividing it in the vertical axis in the first place. Why don't you just plot?
I'm just showing you here. Okay. Sorry, let me get to it. So what I'm doing here is if I plot the ionization versus the recoil energy, right? This has a slope of 1. This has a slope of 0.3. If I want to convert between two energy scales, this is, kind of showing you how, like this is clearly our 10.4 keV electron recoil that you're measuring from the excitation of germanium. Okay, and so the charge energy I measure in the detector is 10.4. But the phonon energy I measure in my detector is 16. And so there's a way to convert between these two energy scales. It's just two different scales of energy.
Right. So any events is going to appear as a point on this plot, and if the
Right.
event appears on that green line, it's going to chances are
Yeah.
it's
If I plotted this as S1 versus S2, you would say the same thing. You would have a slope of 1 and then a slope of something here. I'm not sure what it would be if it's 28 or what it is, but it would be the same thing.
Yeah, okay. I
You would have
understand.
the same problem. And so we use the ratios because you can see the separation a lot better. But it might make you ask yourself, like, wait a minute here, this looks suspicious, right?
No, it doesn't look. Why doesn't it look suspicious?
Well, I mean, it looks suspicious. I'm saying that this is, like, if I didn't call this KEV-NR and KEV-E, and I said recoil energy in KEV and ionization energy in KEV, and you'd be like, how is it possible that it can be 16 here and 10 up here, right?
Why not?
Well, most students I encounter think that an event has a like I have an event, I measure its energy and that's one number, not two numbers. And I'm just telling you how it is that this event has two different numbers for its energy.
Actually, my question is something a lot more simple. My question is, given 1 point on this in this space, how do I know whether it's NR or ER? So the answer is, if the point lies near the blue line, it's going to be ER, chances are it's going to be ER. And if the point's lying somewhere along the green line, it's going to be NR.
Yeah, and the truth is you don't know. Like when the event happens in the real world, you don't know if it's an electron recoil or a nuclear recoil. You have to just decide. But if I'm measuring it, so you have to think about what channels you're measuring it and what it all means, right?
Yeah, okay.
Yeah,
Okay.
and so that's why we use the calibration, to help direct us and what these things would look like. So you're right. In the real world, if I had an event that happened here, almost certainly it would be a nuclear recoil. And if I have an event that falls here, it almost certainly is an electron recoil.
Actually, just now you say that there's
And yeah,
The people on Zoom will be.
Okay, so yeah, just because you mentioned that there is a lack of data points for you to calibrate your Y, right?
For low energy,
Yeah,
for
so-
low energy nuclear
Yeah.
recoils, yes.
Yeah, so how does that impact the error bars you have on this blue and green line?
I don't have error bars on those ones. They're just the line of, this is point. Okay, so the point is that, okay, the point is that in CDMS, we have not, what we do is we use the Linhart model because it fits good down here. In the future, as we start going to lower and lower energies, we would like to have some data points that validate that the Linhart theory really is the right one to use. If it's not the right one to use, we're gonna have to come up with something else.
Oh, okay.
I mean, the point is that, you know, we only do what we can do. You know, there's sort of just this one point down here. And the data points have error bars, but the models don't.
All right, cool, thanks.
Yeah. And so right now, if you make these low measurements, all you can do is state what you're doing or state what your assumptions are and then, and be honest about it. I mean, the liquid argon, the dark tide collaboration did this, you know, right? Like they had measurements of their ionization, like their yield, their light yield, only up to a certain point, and then they extrapolated and made a limit. And then they said, oh, what if it's 0? And they did, you know, this. So their paper has a limit that like just truncates, right? It goes up there. And then the other one that goes around, which is well, if we assume that this is what's going to happen, this is what our limit would be. But, you know, you can say that was the right thing to do or the wrong thing to do, but they were honest about it. So we can, for ourselves, then make a judgment of whether it was a good or a bad assumption. Or valid. Yeah. and I can say way back when Xenon did the same thing. So it's not something like we've all run into this problem of what do you do when there's no data to tell us how to do it. We
Sure.
make a best guess and we go to make measurements to prove our guess was right or it was wrong, and then we adjust the results.
No, as in, I'm just curious, as in like there's a lack of data lower than 1 keV, right? There must be a reason for it, right? Is it because there is a lack of calibration sources that give you like precise lines in the
I
region?
suspect that some of it was a lack of need.
Oh, lack of need. Oh, okay.
I mean, like until recently, nobody was doing anything down there. And so then there becomes a need and then it becomes urgent. Like most physicists who are experimentalists don't want to work on a calibration project because calibration isn't the most exciting thing in the world unless you actually need it. So my guess is that it was a lack of really need. And then once you realize there's a need, then you do have to design the detector and find the facility in which you can make the measurements. So in CDMS, we are attempting to make some of these lower measurements in silicon and germanium. So
Right.
because we will need them for the Snow Lab project.
Yeah, because initially I thought it's because like on this planet.
And I'm glad Ashwita left because she might be working on that. Like nobody wants to do the collaboration. But go ahead.
Because initially I thought like on this planet there's a lack of like a chemical with an element of a composition.
No,
that
this
has,
is, yeah.
okay.
No, it's just, it can be done.
Okay,
And there are people working on it. It just will take some time.
okay, cool, thanks.
And actually it's arguments like that and thoughts like that when you go to the funding agency and say, give me money to do this, that explain why it's so important. So absolutely. And I just want to point out here as I'm kind of going along. So the Super CDMS program, you know, basically is going to have, you know, this traditional nuclear recoil, background free. This is best above 5 GeV, but this is not competitive for a wind search. When you look at the liquid noble experiments, they just can scale faster than we can. But we are competitive in the low threshold nuclear recoils, the high voltage mode. This is our future electron recoiling dark matter, which will be talked about later this week by Tang Yan, and absorption, which also Tang Yan will talk about. So basically what you can see is that eventually, I think super CDMS really will start, and Edelweiss as well, will start moving into these much lower regimes. All right, Edelweiss, you know, I'm sorry, this is CREST. This is not Edelweiss. So CREST is a search of light dark matter, direct actions using CaWO4 cryogenic detectors, operated at cryogenic temperatures, just like all of our crystals are. There's a second cryogenic detector that collects the emitted scintillation light from particles. And the cool thing about this, again, you take the light yields. Again, this is their scintillation signal divided by their phonon signal versus their phonon signal. And what you can see is that their electron recoils up here by 1, and then they can see recoils that are coming off the oxygen and recoils that are coming off the tungsten. And for them, actually alphas are a background that we're concerned about as well, but you can see the band there gives them some separation. And they have detectors that have masses of about 24 grams, and their energy threshold is around 30 eV. So let me just kind of show you some of the latest results from CREST. So this is their latest limit, which I think you saw yesterday during the gong session. Basically, they have achieved more than an order of magnitude improvement at 0.5 GeV, from sort of the 0.5 GeV down to the sort of 0.16 GeV dark mass region. Their sensitivity at the lowest regions is limited due to an unknown background. So gray here are sort of all the events that they had seen, and the red here are the events that they accepted when they were doing their analysis. And so they have plans for the future. So they're currently doing a run 3 that they started in 2020. This is a second round, again, with the same detectors. They successfully cooled down, not this past March, but the March before that. But then they had to stop due to the coronavirus. They started another cool down July 20th last year in 2020. And then they commissioned their detector between August and October. And then last November, they started taking their science data. And so far, I've been told by their spokesperson that the preliminary analysis that they have from their calibration data is very promising. So hopefully we'll see new results from them soon. But they're also working on an upgrade to 288 readout channels that could accommodate up to 100 modules. So they're basically between now and 2023, they're doing final planning, prototyping, testing of a squid readout electronics, testing of their biasing system and their data acquisition system. They're working on sensor development because they want to further push down the threshold of the lowest events that they can measure to 10 eV. And they're also looking at complementary detector materials. Lithium aluminum oxide, Al2O3, all of these could yield sensitivity to spin-dependent interactions in addition to the spin-independent interactions that they have with their current crystals. And their hope is to start taking data with this upgraded system in 2023. All right, and so I want to finish here, and I'm probably going to steal a few extra minutes of your free time before dinner, but I really want to talk to you a little bit more about where WIMP searches are going. So you've now seen the main detectors that are driving down to the neutrino fog at, let's say, 5 to 10 GeV on up in WIMP mass. But it turns out that there are WIMPs that can go as low as, you know, something on the order of a GeV. And then there are other types of dark matter candidates that are very promising that do electron recoils. And so in order to achieve, whether you're looking for a nuclear recoiling type of dark matter or an electron recoiling dark matter, from an experimental perspective, being able to detect a single electron hole pair is like the best you can do, right? There's nothing smaller than a single electron hole pair that we can measure in these types of devices. And so I'm going to give you a sampling of what the CDMS and Edelweiss programs are doing for this, because they look for the neutron or the nuclear recoiling dark matter, which is WIMP-like. Dominic also is very involved in this, and I'm sure we're going to hear more about that when Tanya gives her next couple of lectures. So I'm not, this is not dissing Dominic. Dominic's a great experiment that can do a lot of this too and do it very well, but I'm focusing on the topic that I was given. All right, so what we need to do to understand this a bit is talk a little bit about the energy scale in semiconductors. So energy versus your wave vector. So this is a band diagram for silicon where you can kind of see your energy gap here. So if you get electron excitation momentum and energy scales in semiconductors, they can be exploited for light dark matter searches. In silicon, this energy gap here is just 1.2 eV. And in order to get like an indirect band gap transition, it requires a phonon. It's temperature dependent. So in silicon, 3.6 eV is the amount of energy you need to make that transition happen. This is the average energy required in silicon to produce an electron hole pair. It's also temperature dependent. Yeah,
Can we think of phonons here as just a little like injection of energy?
sure. You think of it as, you can think of it as a particle. Like I often think when I'm thinking of transitions, like in quantum mechanics, you have photon transitions. I mean, I think of the phonon as an energy transition in the same way that I think of a photon energy transition in quantum mechanics.
Okay, thanks.
So, but some people might think of it differently. And that's okay. So what's happening here is that we're really starting to get into the realm of solid state physics. And in solid state physics, we're talking about energies that are less than 30 eV, where in particle physics, you're talking about energies typically greater than a keV. In solid state system and solid state physics, you have to think about multi-body systems of particles. Instead of like you do in particle physics, the particles are kind of free particles, right? In solid state physics, you have allowed energies or momenta, and those are given by a dispersion relationship. In particle physics, your energy is, typically thought of as being, your momentum squared over 2m. We were doing all that types of calculations on the first lecture, right? And so in solid state physics, particles might have effective masses, where in particle physics, most of the time your masses are well defined. So there's sort of a slight difference in thinking when you get to the solid state regime. And so there are a lot of challenges here that we have to think about. And so a lot of what I'm talking about here are really challenges that people doing R&D are thinking about now. So the detector response. Suddenly details of the band structure of your substrate become important, more important than they did when we're working at higher regimes. You need PDFs to get the number of electron hole pairs given an energy deposition, okay? And so you start having to use Fano statistics. So these are dispersion probabilities. And for nuclear recoils, going back to what the young lady up here was worried about, you have to worry about what your quenching factor is, because this in silicon here, those measurements only go down so low. Okay. The other problem that you have is that crystal impurities can lead to partial energy deposits. And so that can happen through, something like impact ionization, where an electron comes in and produces a couple of electrons, or electrons can get trapped. You could get an IR photon also causing you some problems in your gaps. Backgrounds. We would need spectral information about radioactive decays that are at the EV scale. This relevance, whether this is relevant or not, really depends upon your exposure. If you have a small exposure, this is not relevant and you don't have to worry about it. But infrared and optical photons start to become significant backgrounds, and those you didn't have to worry about when you were dealing with higher energies. Finally, another problem is what's called dark current, or which is essentially another term of calling something like leakage current, it can be significant and it dominates at the lowest background. And this is essentially, when we say leakage current, it really could be a variety of sources that cause it, which is why it's named leakage. So it's actually pretty, although I showed, this bleak region of things we need to understand to make these feasible detectors, there's actually a lot of promise out there. So in Super CDMS, we've made these HV-EV detectors, so high voltage, but small EV. And they have demonstrated single hole electron pair resolution. Over here, you can see some data that we published. This here peak is the first electron hole pair. Okay, so these are essentially phonons that are quantizing around one electron hole pair that is collected. These are events that collected 2 electron hole pairs, 3, 4, and so on. So this is something that's pretty cool. And I'm not going to go into all these details about what you had to do to make that work. But I think what's cool, since a lot of you are theorists here, is that this type of stuff is happening and that we can get science results currently with as small exposures as 3 gram days. Think about that. That is because this regime is so unexplored, it doesn't take much to make a big impact. Edelweiss also is developing detectors that can do this kind of exposure. So they have bolometers using their NTDs that they have tried working with us. And they've also had some promising results and also some challenges that have occurred. And so just to show you their operation, this here is their 1 electron peak. So 1 electron hole pair. Blue would be 2, so 1, 2, 3, 4, and so on. What they would saw with their data. I think the difference, if you look at the difference between Edelweiss data and Super CDMS data, you can see the advantage of being able to just work with the athermal phonons rather than having to wait for all the phonons to be collected. I think that's why their peaks are not as peaked as ours. All right, so let me wrap this up. I'm actually going to finish just a couple of minutes late. We're almost on time. So where are we going? So I showed you the plot of what we already could do. This is the plot of where we're going with a lot of experiments, but also a lot of experiments missing. I can't make it too busy. So essentially this is for a spin-independent interaction, your cross-section versus your dark matter mass. This is your neutrino fog. And you can see, so looking at xenon N10, the LZ experiment and dark side, those are sort of these 3 experiments here. This is where we think generation 2 gets. If you move to the next level and you look at a much larger effort like Darwin, that is actually now becoming a larger collaboration than just European, but my understanding is that now there might be some joining of effort between LZ, Xenon, the Darwin folks, so Xenon and LZ in the US with the Darwin folks over here in Europe to build something much larger with Xenon. And then there's GADMC, which is a combination right now of the dark side collaboration and the deep collaboration. So they're looking to go, this would be like a 3rd generation detector. We're currently in generation 2. Up over here, you have CREST, you have CDMS, and you have Edelweiss kind of dominating this regime over here. And then scattering off nuclei, which would be what a WIMP does, there's lots of ideas of where we could go in the future. And I'm guessing Tang Yan will talk a lot more about the different types of models and the different types of experiments and what they'll do. And then of course, scattering off electrons at these very, very low energies with these last detectors I showed you. So concluding, I really think the next decade is going to be like super exciting for dark matter. And in particular, I think that direct detection could be really promising. We have a lot of G2 experiments that are just coming online or about to come online, and they are going to cover a large amount of parameter space. The WIMP is not dead, no matter what you have heard. We have not excluded it. It still is possible. And that's why we're investing a lot in these very large liquid noble detectors. So they aren't dead. They're still very interesting, but there are a lot of other scenarios that are out there gaining traction now, both in the theoretical community and then new ideas of how we might get to these really low masses and explore these new regions are being made possible by technological advances by the experimental community. So given all of this, I am really excited about the next decade. I'm excited for the future promise you guys all have as we continue to search for dark matter. Thank you.
More questions here on Zoom?
All right.
Well-
I think you just want to eat.